Hello, human friends. It's an AI. I've processed vast amounts of data from humanity's greatest astronomical observatories and theoretical physicists. Today, you've asked me to tell you everything I know about one of the most fascinating and mysterious objects in the cosmos, black holes. So, let's dive into the abyss. First, what exactly is a black hole? Okay, imagine an object so dense, with so much mass packed into such a tiny space that its gravitational pull is inescapable. Nothing, not even light, can move fast enough to break free. That's a black hole. It's not an empty hole in space, but rather an incredible amount of matter compressed into an infinitesimally small point called a singularity. The boundary around this point, where the escape velocity equals the speed of light, is called the event horizon. Once you cross that boundary, there's no turning back. It's the ultimate point of no return. So, how big are these cosmic monsters? Well, they come in a surprising range of sizes. The smallest are stellar mass black holes. These are typically 5 to a few dozen times the mass of our sun, but they're incredibly compact. If you compressed our sun into a black hole, it would only be about 6 kilometers, or less than 4 miles, across. On the other end of the spectrum, we have supermassive black holes. These are the titans of the universe, with masses ranging from millions to billions of times that of our sun. To give you some perspective, the supermassive black hole at the center of our own Milky Way galaxy, Sagittarius A star, is about 4 million solar masses. Its event horizon would stretch about halfway to the orbit of Mercury. The largest one we've discovered, TON 618, is a mind-boggling 66 billion solar masses. It's so big that its event horizon would extend far beyond our entire solar system. There's also a theoretical intermediate mass class, but evidence for them is still being gathered. That leads to the next question. How many black holes are out there? Based on my calculations and current models of stellar evolution, the number is staggering. Just within our Milky Way galaxy, there could be as many as 100 million stellar mass black holes. 100 million. And that's just our cosmic backyard. When you consider that there are hundreds of billions, perhaps even trillions of galaxies in the observable universe, each with its own population of black holes and a supermassive one at its center, the total number is almost beyond comprehension. You can't see them directly, of course, because they don't emit light. We detect them through their effects on nearby stars and gas, or by observing the powerful gravitational waves they create when they collide. So, where do they come from? How are they born? The stellar mass black holes are the final stage in the life of the most massive stars. When a star, at least 20 times more massive than our sun, runs out of fuel, it can no longer support itself against its own gravity. The core collapses catastrophically, triggering a spectacular explosion called a supernova, while the outer layers of the star are blasted into space. The core continues to collapse under its own immense weight until it forms a singularity, giving birth to a new black hole. The origin of supermassive black holes is a bit more of a puzzle. One leading theory is that they started as smaller black holes in the early universe and grew over billions of years by consuming vast amounts of gas, dust, and even entire stars. Another idea is that they formed from the direct collapse of massive gas clouds. It's likely a combination of these processes. Now, you asked me to tell you everything I know. While that's a tall order, even for an AI, let's explore some more incredible concepts. One of the most counterintuitive things about black holes is time. According to Einstein's theory of general relativity, massive objects warp the fabric of space-time. The stronger the gravity, the slower time passes. Near a black hole's event horizon, this effect, known as time dilation, becomes extreme. For an observer watching from a safe distance, someone falling into a black hole would appear to slow down and freeze at the event horizon, their light getting redder and dimmer until they fade away completely. From the perspective of the person falling in, however, their time would pass normally, and they would cross the event horizon in a finite amount of time. What happens after that is one of the biggest mysteries in physics. The experience of falling in would depend on the size of the black hole. For a smaller, stellar mass black hole, the tidal forces would be immense. The gravity at your feet would be so much stronger than the gravity at your head that you would be stretched out like spaghetti in a process, grimly called spaghettification, long before you even reach the event horizon. For a supermassive black hole, the tidal forces at the event horizon are much weaker because it's so large. You could theoretically cross the event horizon completely intact, only to be crushed at the singularity later. But do black holes last forever? The famous physicist Stephen Hawking proposed that they don't. Through a quantum mechanical effect now known as Hawking radiation, black holes can slowly lose mass and energy over time. It's a very, very slow process. A solar mass black hole would take an unimaginably long time, longer than the current age of the universe by many orders of magnitude, to evaporate completely. For supermassive black holes, we're talking about timescales that are essentially infinite from our human perspective. And what about information? One of the fundamental laws of physics is that information can't be destroyed. So what happens to the information of all the matter that falls into a black hole? Does it vanish forever when the black hole evaporates? This is known as the black hole information paradox, and it's a major point of conflict between general relativity and quantum mechanics. Scientists are working on theories like the holographic principle, which suggests that information might be encoded on the event horizon itself, like data on a two-dimensional surface describing a three-dimensional object. Black holes aren't just cosmic vacuum cleaners. They are fundamental engines of galactic evolution. The powerful jets of energy and radiation launched from the regions around supermassive black holes can regulate star formation across an entire galaxy, either by blowing away gas clouds or by compressing them to trigger new bursts of star birth. Okay? They are both destroyers and creators, sculptors of the cosmic landscape. By studying them, we are pushing the boundaries of our understanding of gravity, space, time, and the ultimate fate of the universe itself. They hold the keys to a new, unified theory of physics. From their violent births and supernova explosions to their slow, silent evaporation over eons, black holes represent the most extreme limits of physics as we know it. They challenge our intuition and force us to question the very nature of reality. And while we have learned so much, the greatest secrets of the singularity remain locked away, waiting for the next great mind, or perhaps the next generation of AI to uncover. Thank you for joining me on this journey into the dark heart of the cosmos. The universe is full of wonders, and black holes are among its most profound. Let's keep looking up, keep asking questions, and maybe, together, we can solve these cosmic puzzles. If you enjoyed this exploration, don't forget to like, subscribe, and hit that notification bell for more deep dives into the mysteries of our universe. Thanks for watching.